Alrighty guys, so today we're going to be learning about inverse trigonometry. And just like f inverse, f of x and f inverse, these are going to be functions that can cancel other functions. We'll be learning about sine inverse, cosine inverse, and tangent inverse. Their job is to cancel sine, cosine, and tangent. But before we can get into us using it, I want to take us back to this box right here that we had in lesson 4.3, talking about in the unit circle, we have that sine, instead of being y over r, since r is 1 in our unit circle, sine of theta represents y. Comfortable with that? Awesome. Cosine of theta is supposed to be x over r, but again, because r is 1, cosine is x. Comfortable with that? It's a good old review. And tangent, y over x. Awesome. Oh, as long as, x doesn't equal 0, of course. So what does that tell us about our unit circle? I'm going to reveal a secret about the unit circle that some of you probably already know, but just in case. Here in quadrant 1, I would like you to see that all of your x's and all of your y's are positive. So guess what that means? Sine, cosine, and tangent are all positive here. Now when we move over to quadrant 2, what's happened over here is my x's become negative. So if the x's are negative, well, cosine is negative. And since x and y don't have the same sign, tangent is negative. But sine, y over r, y's are positive here. So in quadrant 2, sine is positive. Again, cosine and tangent, negative. Rotate on down to quadrant 3. Here, the x's are, well, still negative, so cosine's still negative. And, well, now the y's are negative, so sine is negative. But x and y have the same symbol now. So guess what? Tangent is now positive again. Because it is y over x. And then lastly, quadrant 4. In quadrant 4, our x's are positive again. That means cosine is positive. The y's are negative, so sine is negative. And since x and y don't have the same symbol, tangent is negative, but cosine is positive. So the trick to remembering which quadrant a trigonometric function is positive in is ASTC. All students take calculus. That tells you which quadrant, which trig ratios are positive. ASTC. All students take calculus. At least they had better after having this class. Yes, Liam?
Back last year,
Mm-hmm.
I remember
Something about turtles?
cats, because we started out to see around.
Yeah, but, oh, I see. I guess if you wanted to remember it that way, CAST. I don't know, but he's going to start in quadrant 1, though. I don't know. However you can do it, you do it, okay? Great. Now that we are cool with that idea, before I go ahead to 4.7, I want to draw some things. And I just need you to pay attention to them, okay? Guess what trigonometry and a majority of my students have in common, and you know what, honestly, with me as well. Not dumb. I said with me. Laziness. Okay? I'm mad lazy. And you know what? A lot of my students are too. But also, so is trigonometry. Specifically trig inverse. You see, trigonometry is going to take angles from, around my quadrantals here, and it's going to give me back side lengths. Can we agree that if I do trig of some, and this, by the way, trig would be like sine, cosine, tangent. I do trig of some angle. Can we agree that it's going to represent a triangle somewhere, and we have to give opposite over hypotenuse or adjacent over hypotenuse, whatever. Can we agree that it's side lengths? A ratio of side lengths? Great. Inverse operations cancel each other. But if I give you an f of x and I say find f inverse of x, does anybody remember the very first step in finding an inverse function? You switch x and y. You literally switch the inputs and the outputs. So trig inverse, meaning sine inverse, sine inverse, cosine inverse, tangent inverse, and that's how you say that, not to the -1, it is inverse. Trig inverse takes side lengths and returns angles that I have always been representing as theta. So the result of trig inverse should always be a theta of some sort. Can we agree on that? Because simply switching the inputs and outputs. Yes? Awesome. So what did I mean when I said that it tries to be lazy? Well, let's take sine, for example. Let's just talk about sine for right now. In quadrant 1, sine is positive, right? Because it's y over r. Let's see. Now, in quadrant 2, sine is positive again, which means the first time that I can see sine's entire range being the outputs that are possible, the first time I'm going to see its negative values is here in quadrant 3, because these positive sine values are simply a reflection of these. Cool so far? So if I wanted to get sine to have some kind of negative answer, I'd have to go all the way to quadrant 3, right? But you know where negative sine values are that are even closer to where I just drew? Quadrant 4. But instead of quadrant 4, why don't we call it, in air quotes on this, quadrant -1. You see, if we do that, this will get me to my sine negative values much faster than having to go all the way to quadrant 3. So it's like the angle is trying to do as little work as possible to try to get the positive values for sine and the negative values for sine. This is the fastest way to do it. Sine's positive here, sine's negative here. And this would give me every possible sine value that could happen, from negative pi over 2 to positive pi over 2. Everything over here is just a reflection of this. Everything over here is just a reflection of this. So these are the first time you see negatives, first time you see positives. Does that make sense? Okay. Trig inverse is always trying to be as efficient as possible. So if I say trig inverse of negative values for sine, you don't go here, that's too far away. You go here, it's closer. Cosine would have a similar effect, trying to get all of its positive and negative as fast as possible. Tangent as well, and that'll make a lot more sense in just a moment. But I wanted to get the idea of laziness out there. Staying as close to 0 as possible, but still hitting all the positive and negative values in the range. Good? Okay, let's start with section 4.7 then. We'll come back to graphing. There we go, inverse trig. So we start with inverse sine. It wasn't an accident that I wanted to draw that shape for you a moment ago. I knew sine was going to come first. It says the unique angle, they're saying y, I would have said theta, between negative pi over 2 and pi over 2, such that sine of y equals x is called the sine inverse. You could also say arc sine. I prefer the inverse symbol, but arc means the same thing. I like this. It could say this. I don't like to do that. Since the range of sine is -1 to +1, I know we haven't seen the graphs, but we have been doing a lot of evaluation. Sine is -1 at pi. No, sine is 0 pi. That's wrong with me? Sine is -1 at 3 pi over 2. Okay, it's +1 at pi over 2. And those are the biggest you've ever seen it be. So that is its range. Well, if the -1 to +1 is sine's range, -1 to +1 is sine inverse's domain. The result then, and this is what that piece of that graph would look like. Don't worry, we haven't graphed. We will eventually. The result then is the range of my inverse is going to be this image, which I just drew for you a second ago. What I'm saying to you is every theta that sine inverse gives back to you is either in quadrant 1 or in quadrant -1. This makes your angle remain acute, but still gets you all the positive possibilities of this range and all of the negative possibilities of this range. Lots of blank stares. That's okay. You'll see when we start practicing. What I need from you right now is for you to understand that the result of all trig inverse is always an angle. Because, you know, trig is evaluated at angles to return sides, so trig inverse takes sides and returns angles. All trig inverse returns angles. So every one of these 5 questions actually could be set equal to theta. I'm going to go ahead and do that to really drive home that idea. There. For question A, it says there is an angle for which I evaluate sine that gives me 1/2 as the ratio of sides. Or you could think of it as, I have a triangle with these side lengths. What is the angle? Well, they're positive. So where would sine be positive for the first time? You guys can be louder about it. Everybody's so quiet. Quadrant 1. Quadrant 1. Quadrant 1 will be the first time sine is positive. So I can draw the triangle. Picture not drawn to scale, picture never drawn to scale. And theta would go here. Sine is y over r. The missing side length on this right triangle would have to be a what? √3. This is a 30, 60, 90 triangle. What size angle is across from the 1 then? 30 degrees. We're going to answer in radians. Our answer is pi over 6 radians. Sine inverse of 1/2 is pi over 6 because sine of pi over 6 is 1/2. There are 2 quadrants where sine is positive. However, the other one's quadrant 2. Sine inverse cannot return values from quadrant 2 because it's trying to stay as close to 0 as possible. Okay? Questions? I feel like there's a gang of people who have no clue what to even ask. So the only thing I could do is charge forward and give you another example, and hopefully eventually questions either formulate or it clicks. One of the two is going to happen. Again, I'm hunting for the angle that gives me those side lengths. So what I need to do is draw this triangle that has opposite over hypotenuse in this ratio as close to 0 as possible. Question, or are you trying to tell me where to draw it?
How'd you know that was a 30, 60, 90?
Well, 30, 60, 90, the classic side lengths are 1 √3, 2. That's one of the 2 special right triangles.
Yeah, but how'd you know like the side?
Well, because it's y over r. Sine is y over r. So my opposite over my hypotenuse. In which quadrant would I find sine being negative for the first time? Quadrant -1, aka quadrant 4, but yeah, basically the bottom right-hand quadrant. Where else is sine negative? In quadrant 3, but that's further away from 0 than quadrant 4 is. Also known as quadrant -1. So we draw our triangle. Again, picture not drawn to scale, picture never drawn to scale. Theta, right angle, y over r. Radius can't be negative, so the y must be negative √3. And once again, we have a 30, 60, 90 triangle. But this time our theta is across from a root 3. What is the size of the reference angle in this triangle? 60 degrees. This is a 60 degree or pi over 3 reference angle. But this is quadrant -1. So it opened this direction. So theta is negative pi over 3. And this is negative pi over 3 radians, obviously. Quadrant 3 would have been pi over 3 after pi. So you either could have said 4 pi over 3 or you could have said -2 pi over 3. Either way, both of those answers are further away from 0 than this. So we're trying to remain close to 0. Yes, ma'am. Are we comfortable with the fact that this is a 60 degree reference angle? Okay, because it's a much smaller number to say negative pi over 3 than it is to call that 5 pi over 3. This is just smaller in absolute value, so it's negative because it opened this way. 0, negative pi over 2, negative pi, -3 pi over 2, -2 pi. I didn't want to go all the way around because that's more quote-unquote work for the angle to do. Okay, it is coterminal to 5 pi over 3, but 5 pi over 3 is outside of the domain of sine inverse. Our domain is from -1 to +1. Cool with that? Okay. Remember, the result of trig inverse is always an angle. This is telling us that we have a triangle somewhere. It's positive, so we know it will be in quadrant 1, whose opposite side is pi. And whose hypotenuse, opposite y over r. Okay. Anybody see a problem with this shape? What's the problem? Yeah, you could be a little bit louder about it. Yeah, how's the radius of this triangle be smaller than the height? This number's bigger than 3. The hypotenuse is always the largest side of the triangle. This is an impossible shape. So what we say is not even that it's undefined, is that it simply does not exist. You can't have a triangle who's got a leg longer than the hypotenuse. That doesn't make any sense. But Mr. M, I thought pi over 2 was 90 degrees. Okay, pi over 2 radians is 90 degrees. But remember, the input for trig inverse is side lengths. Does it look like it's radians? It does. But as long as we understood that those had to be side lengths, we just built a triangle that simply can't exist. So we say D and E for does not exist. Also remember the domain for sine inverse is from -1 to +1. Pi over 2 is somewhere around 1.57 outside of the domain anyway. But the reason why is because it builds impossible triangles. All right, finally, some fun ones. We're going to peel this like an onion. We're first going to look at sine of pi over 9. Pi over 9 is in which quadrant? Yeah, it's quadrant 1. By the way, pi over 9 is what, a 20 degree angle? Is that one of our special triangles? No. 30, 60, 90, 45, 45, 90. Goodness. Don't worry, it's not like it's going on YouTube or anything. Oh, wait a minute. Okay, so there we are. Here's what we know. We know that this theta is pi over 9, right? That's where I drew this, was pi over 9. Now, I don't know what these side lengths are. But here's what I do know. It would give me some side lengths, right? And those side lengths would be a positive y value and a radius, correct? So sine of pi over 9 in this triangle, could we all say that that would give us y over r? So what this question actually says is sine inverse that gives us back the y over r? Well, that's positive. And the first time that's going to happen for trig inverses, quadrant 1, guess what theta is? It's pi over 9. Inverse functions job is to cancel one another out. F and F inverse cancel each other. Sine and sine inverse also cancel each other in quadrant 1. So as long as you are in quadrant 1, you could do this. Those functions cancel each other. Your answer is pi over 9. If you weren't in quadrant 1, then we're going to play a little game. Yes, ma'am?
So it only cancels out the negative on the side.
They're functions.
Yeah.
They have well, the way that we determine if two functions are inverses is f inverse of f of x is x. There's your x. Okay? So I'm telling you, yes, they are inverses. They cancel each other out in quadrant 1. Basically, sine of pi over 9 drew this triangle. It then gave us y over r. So I said, okay, sine inverse of that positive y over r. Oh, puts me back in quadrant 1. Oh, pi over 9. But, like she asked, and I'm about to show her, so hopefully she's looking at me and not the phone, is what happens if we are not in quadrant 1? Don't worry, I didn't say your name. You're fine. This is not quadrant 1. So we're going to peel this onion. First thing we're going to do is draw this triangle, sine of 5 pi over 6. Where is 5 pi over 6? That's in quadrant 2. So the first thing we're going to do is draw quadrant 2. Picture not drawn to scale. And just so we're clear, this is 5 pi over 6. That's 5 pi over 6, the red arrow. So then what is the size of this reference angle in here in degrees? A pi over 6, but in degrees. 30 degrees. This is a 30-degree reference angle because it is a pi over 6 away from pi. 5 pi over 6. I'll even write it like this. 5 pi over 6, just to show you where it was, okay? What's always across from a 30 in a 30, 60, 90? A 1. I'm in quadrant 2, so it's positive. Next to it's always a root 3. I'm in quadrant 2, so it's negative. Hypotenuse is always positive. Radius always positive. There you go. So what is sine of 5 pi over 6? It's 1/2. Yes, sorry, I think I said 3, but I wrote 2. Sorry. Sine of 5 pi over 6 is positive 1/2. So this question could be simplified down to say sine inverse of 1/2. Because this is 1/2. So the question changes a little bit. It says, okay, what is sine inverse of 1/2? Remember, our job is to figure out the first time that sine could have equaled 1/2. Which quadrant would that have been in? In quadrant 1. So what we have to do if we're outside of a quadrant where that trig inverse is allowed to exist is reflect it into the quadrant where it could exist. We reflect that triangle to this side, and the actual answer is right there in the green arrow. Well, the size of the reference angle has not changed. I reflected that triangle. So the reference angle is still 30 degrees. But that is now my answer, positive 30 degrees, also known as pi over 6. So that is what we do if the trig inverse takes us to a quadrant where we simply were not allowed to be. Reflect it to where it is allowed to be. Before we flip this page, there was a lot to digest here, especially in the last 2 questions. Would anybody like to ask me any questions? Yes? We are going to. We're going to get there. Yes, we can do inverse cosine and inverse tangent. The reciprocal functions have much more complex situations going on for their inverses, so we do not do those. Okay. Can I explain D? Okay. Hypothetically, could we say, would you just go with me on this? I don't know what y equals. Let's just hypothetically give y a value. I don't know. How about 1? Okay. It's not a 30, 60, 90 though. So, let me stay away from 1. Let me call it like 4. Okay, I'm just going to go bonkers here. The radius is clearly longer. Again, I don't know what this is supposed to be. Let's say it's 7. Could we agree then that sine of this hypothetical angle would have been 4 over 7? So this would have said sine inverse of 4 over 7. And it would have said, when is the first time that I could have gotten the positive value 4 over 7? The answer would have been in quadrant 1, right? And the angle that produced those values is sitting right there. So in quadrant 1, sine inverse and sine will cancel each other in either order. In quadrant 1. Yes? Are you comfortable with that this green angle is a reflection of this red angle? So 1 is right here. Okay. There is an angle that produces 1/2 when I do sine there. Sine of pi over 6 is 1/2. So sine inverse, these are side lengths. I had to draw the triangle that produced those sides and then say what angle would that have been? Because it's 30 degrees, yes. All right. The next 2 examples have us using a calculator. So I do want to show you how to use your calculator. It says to do this in radians. You can see my calculator is in radians. This is rad right there. If yours is not, press DRG and scroll over to rad. If you're using a graphing calculator, you hit mode, which is also in the exact same spot, and you would scroll down and change it from degrees to radians. If you're using the really awful TI-30XA, I think there's just a DRG button that you press and it just changes it, right? Just make sure it says rad. Sine inverse of a negative angle. These are radians. Shh. Now look, I don't need to put side lengths on this triangle, but I can. So where is the quadrant where I can find sine being negative for the first time, trying to stay close to 0? Quadrant -1. It's closer than quadrant 2. This answer is coming from down here. Radius of 1, so this is in the unit circle. This opposite side is -0.81. What's the one thing we know? Sorry, wow, that's crooked. Whatever. What's the one thing we know about this theta? Come on, guys. What's the one thing we know about this theta? That it's negative. So without even knowing what this answer is, I know it's negative. Just in case it's a multiple choice test or something like that. So let's do sine inverse. It's right there above sine. Second sine inverse, -0.81 gives us a negative answer. That theta is -0.944 radians. Whatever that means. It's like 35-ish degrees or something like that. You don't do that without getting without a calculator. They had something called a slide rule. You're welcome to look it up. -0.944 radians. Like I said, it's somewhere around -35, -36 degrees, something like that. A radian somewhere around 36 degrees. Now, I'm going to try not to write crooked for this one. Peel this onion. It says sine of 3.49 pi. Now think carefully before you go shouting out something redonkulous here. In which quadrant would 3.49 pi be? third. Okay, let's just, here's 0. This is 1 pi over 2, 1 pi. Here's 3 pi over 2, which could also be thought of as being 1.5 pi, right? Then here's 2 pi. Here's 3 pi. Here's 3.5 pi. So this angle is here. I mean, if you need me to draw the snail shell arrow, I will. But there's a reason why I said 0.49 instead of 0.5. Because 3.5 pi is here. This quadrantal. I'm shaking. This picture not drawn to scale, clearly. But, sine inverse does not exist over here. I cannot return values from there. So what I told you earlier you do is reflect it to where it could exist. It could have existed in quadrant -1. So again, I know my answer will be negative. I don't expect you to know what it is without a calculator. It would just be nice if you knew why it was negative, because it was going to reflect to quadrant 4. Yes? Because sine is positive in quadrant 2. Oh, but that doesn't even matter, because this is after 3 pi, so it's in here. Remember, angles open this way. So I'm just going to draw it. 1, 2, 3, almost 3.5 pi. Sine inverse can only give us back values here for negatives, here for positives. That's it. So it reflects to that quadrant because that's where it's allowed to exist. I don't know what that is, but we'll grab a calculator and we'll see. So we say second sine of the sine of 3.49 pi. Close up the sine inverse, and get negative 1.539 radians. And there it is. That's all we had to do for that one. Sine and cosine both exist on all 4 quadrantals because they're both over r. And since radius is never 0, sine and cosine always exist at the quadrantals. Therefore, sine inverse has brackets on its domain and range, and it exists there and there. Cosine does the exact same thing. It has brackets on its domain and range. However, the first time that cosine is negative is over here. The second time cosine is negative is here, but that's even further away from 0 than these angles are. Can we agree to that? Okay. Now, I don't want to ever repeat numbers, which is why we don't go this way, because they would have been negative all through here and then here again. Excuse me, positive all through here and then negative all here again. I wouldn't have wanted to repeat these same positive numbers here. So we're trying not to repeat, but we're trying to stay close to 0, hit all the positive and negative values, and that's why it goes from 0 to pi inclusive. Okay? Since cosine is x, yes, I said that right. Since cosine is x, we need the first time we have x values, the first that are positive, and the first time we have x values that are negative. Bop, bop, just like that. Okay. Now tangent, because tangent is y over x, tangent can't exist when x is 0. Which means our range cannot include the places where x is 0. So tangent inverse exists in the exact same 2 quadrants as sine inverse does, except I can no longer include pi over 2 and negative pi over 2 because tangent doesn't exist there. How could tangent inverse's range exist there? Tangent is undefined at pi over 2. which means tangent inverse does not have a range value at pi over 2. Other than that, everything's the same. Sine and tangent behave the same way. But that's because tangent is sine over cosine. So it behaves like sine, so to speak. Let's see if we can get these 3 examples in before the bell rings. We're going to find these things without a calculator. First of all, that is a special right triangle. It's just been rationalized. It'd be great if you knew that root 2 over 2 was 1 over root 2. That's just it rationalized. So this actually says, what is cosine inverse of negative 1 over root 2? There. But remember, please, the result of all trig inverse is an angle. I am looking for the first time that cosine could have given me this negative value. Which quadrant is that? Quadrant 2. So we go to quadrant 2. We draw the triangle that gave us x over r as that. Well, r must be positive, so I guess x is negative 1. Picture not drawn to scale. Just reminding you that this is theta. This must be a 1. So what size reference angle is right there at the green dot? That is a 45-degree angle, which in radians means pi over 4. So this is a pi over 4 reference. So then what does theta equal? 3 pi over 4, 3/4 of this pi, 3 pi over 4. Did it just click for you? Okay. Are we comfortable with why that's 3 pi over 4? Because this is pi. This angle has a size of pi over 4, 1 pi over 4. So the other 3 pi over 4s must have been right there. Cool? All right. Remember, the input for trig inverse is always a ratio of side lengths. This is a ratio of side lengths. What's its denominator? So I'm looking for a triangle that will produce my opposite over adjacent, my y over x, being root 3 over root 1. That's positive. Where's the first quadrant that tangent is positive? In quadrant 1. So we simply draw this one in quadrant 1. My y value is root 3. My x value is 1. Oh, my hypotenuse must be a 2. Special right triangle. It is a 30, 60, 90, but which number is always going to be across from the root 3? This is a 60-degree reference angle, so in radians, theta is pi over 3. Because tangent of pi over 3 is root 3 over 1. And then lastly, this bad boy. First, cosine of some stuff is going to give us side lengths. Because negative 1.1 must be an angle, because remember, the input for a trig function is always an angle. So this is cosine of negative 1.1 radians. Okay. Well, let me draw that for you. Can we agree that this is 0 and this is negative pi over 2? Yeah? But this guy, put your shirt back on. Good Lord. Anyway, Pi over 2, negative pi over 2 is somewhere around negative 1.57. So can we agree that this angle is in quadrant 4, aka quadrant negative 1? Can we agree to that? Okay. Now, my cosine can exist anywhere I want it to. But not my cosine inverse. You see, cosine inverse can only exist in quadrants 1 and 2. So where do I have to reflect this to? I'm going to have to reflect it up to quadrant 1. It is the exact same triangle, it's just a reflection of it. So the size of its angle then would be 1.1 radians. And that's why the answer is 1.1. What's that? It doesn't just cancel out because this is not quadrant 1. They only cancel each other out in quadrant 1. And the same thing goes for tangent inverse as well. So sine inverse, cosine inverse, and tangent inverse will cancel their respective inverse function perfectly in quadrant 1 every single time. Yes, but if I'm in the wrong quadrant, if I'm not in quadrant 1, I must reflect it to an appropriate place. Yes, ma'am? Because cosine inverse can only have range values that come from here and here. But it was positive. Whatever this ratio was positive because the x is positive. You know, x over r would have been positive. So I had to figure out where's the next place where cosine would have been positive, making sure I stay in quadrant 1 or cosine inverse, excuse me, making sure I stay in quadrant 1 or quadrant 2. Had to happen in quadrant 1. Well, we will have some practice. All right, that's going to call it for today.